Welcome! In this video, we'll be discussing constructibility in Euclidean geometry. Specifically, we'll be answering the age-old question of whether it's possible to do the following three tasks using only a ruler and compasses. So the first one is called squaring the circle, the second one is called doubling the cube, and the final one is called trisecting the angle. These are some questions that have, occupied the ancients for quite some time, and we can answer them using modern abstract algebra. In fact, we'll prove that none of these three things is possible, but before doing this, I need to describe exactly what we mean by constructions using ruler and compasses. The idea is that we start with certain points in the plane. For example, I might be given these 2 points A and B here, and then we have two tools, namely the ruler and the compasses, which allow us to perform two different tasks. First, the ruler allows us to draw a line between any 2 points we've already constructed. So in this case, I would be able to draw a line through A and B, like so. Aside from this, we can't use the ruler to do anything else. In particular, the ruler isn't marked, so we can't use the ruler to measure things. So maybe instead of thinking about like a modern ruler with like a measurement scale on it, you should think more of just like a straight piece of wood. Moreover, we'll think of all the lines we're drawing as extending to infinity. So even if I draw a line segment, this just means that I'm only interested in that specific part of the actually infinite line. In particular, this means that if we already have a line segment, we should think of that line segment as being embedded in the longer infinite line. So in particular, we can always extend a given line segment to make it longer. All right, so that's the first thing we can do with the ruler. And then the second tool we have is the compasses, which allows us to draw circles. Specifically, we can choose a point we've already constructed as the center of the circle. For example, A could be the center. And then I can choose a second point that I've already constructed as defining the radius of the circle. In this case, I would choose the point B. And then using the compasses, I'm allowed to draw a circle around A that has radius AB. Finally, whenever the objects we've constructed, such as circles and lines, intersect, we get new points. For example, here this intersection point of the pink circle with the orange line gives me a new point, which I'll label C. And then, of course, these new points can again be used to construct new lines and new circles. Now, the amazing thing is that, as Euclid shows in his books, you can actually do really complicated stuff just using these two tools. As an example of a construction that gives us some interesting object, let's consider one of Euclid's first propositions, namely how to construct an equilateral triangle. So for this, we again suppose we're given 2 points, A and B, and perhaps we can already assume that we're given the line segment going from A to B. This doesn't really matter because if it wasn't given, we could just draw the line through A and B. And now our task is to construct an equilateral triangle that has base AB. Now the way to do this is to first fix A as the center of a circle and draw a circle with radius B. And then we do the same thing, fixing B as the center and taking the radius to be A. We draw another circle. Now we get 2 intersection points of these circles, which we can label C and D. And we can use any of these to construct the equilateral triangle. So let's choose C. And what we then do is we draw a line through A and C. And then finally, we can draw a line through C and B. And this gives us the desired equilateral triangle. Why is it equilateral? Well, if you think about what we did, so the distance from A to C was given by this circle we drew, which had radius AB. So this length here is the same as this length. And similarly, the distance from B to C is given by this circle with center B and radius AB. So this length here is the radius of the same circle as this one, and so they're also the same, which means that all 3 sides of this triangle are equal. Notice also that this construction actually gave us a bunch of other intersection points, so we get an intersection point down here and one here, but we've just ignored those because they aren't important for continuing the construction. But in principle, we could also use these new intersection points for further constructive work. Okay, so this is an example of something that is possible to construct using only a ruler and compass, namely we can construct this equilateral triangle on a given base. Now let's turn to the three problems that have been stumping people since ancient times and give an exact description of what's required in order to satisfy them. So the first one is called squaring the circle, and the idea is that you're given some circle, and well, from the circle we already have its center, let's call this O, and let's say we also have some point on the circle A, so we have its radius. And now the question is whether we can construct some square. So we want to somehow construct a square that has the same area as this given circle. So this would involve constructing these 4 points here, and then, well, we get a square by joining them with lines. Now, of course, the tricky part here is to get exactly the right length of this segment so that the area of this square here is exactly the area of the given circle. Now, although Euclid doesn't really think about numbers as being assigned to areas, we can still do this and think about this problem analytically. So if the radius here of this line segment defining the circle is r, then we know that the area of the circle will be pi times r squared. And therefore, we want, well, the square to also have area pi r squared. So we know that one of the side lengths here would have to be the square root of this, so it would have to be square root pi times r. And well, investigating this thing analytically already might give a hint to why this is not possible, and the reason has something to do with this number pi here, which would have to be constructible. So if you think about it, the procedure we have of drawing lines through given points and then drawing circles will only give us certain numbers, and well, it turns out that pi is not one of the types of numbers we can get. The next problem, called doubling the cube, goes as follows. So here we assume that we're given some fixed cube, and well, this has a given volume, let's say V. And now the question is whether we can construct a cube which has exactly twice the volume of this original cube. So we want to somehow perform a construction and get a cube that's slightly larger and has exactly twice the volume. Now let's assume for the time being that this cube actually has some volume 1, so this means that one of the side lengths is like a unit element. Well, in that case we would want our doubled cube to have volume 2, which would mean that the side length of this new cube would have to be the third root of 2. Now the third root of 2 is a little less special than the number pi, but it turns out that it's still not a type of number that can be constructed using just the operations we can perform with ruler and compasses. Finally, the third problem is one of trisecting angles, which is pretty much what it sounds like. Namely, we're given some angle, and now a trisection of this angle would be we draw a new line like this, so that the angle between this new line and one of the original lines, so let's call this alpha, is exactly 1/3 of the original angle. So in that case, our original angle would be 3 alpha. Again, Euclid wouldn't have phrased this in this form, but instead he would have said that we trisect this angle, so we draw like 2 lines such that we get 3 angles where we originally had 1, and well, each of these new angles should be equal. So each of these angles should be congruent to one another. If we assign numbers, then we would say that each of these angles is equal to alpha. Now in this case, it's actually possible to trisect certain angles, but it's not possible in general. So in all of these cases, there might actually be special, circles or cubes or angles which we can perform this construction on, but the idea is that we have a general construction that works for all cases, and this is impossible for all these 3 problems. In the last example, for instance, we can show that it's not possible to trisect an angle of 60 degrees. So in other words, it's not possible to construct an angle of 20 degrees given an angle of 60 degrees. Again, in this problem, the reason why it's not possible will have something to do with a specific number that cannot be obtained from the steps we're allowed to take using ruler and compasses. Namely, in our case, the angle of 20 degrees will not be constructible because this number, cosine of 20 degrees, is not one of these numbers we can get using rulers and compasses. As I already foreshadowed in describing these problems, the way we're going to use algebra to prove that they're not possible is that we're going to relate constructibility in the geometric sense to certain numbers that we can obtain using the construction. So the idea is that we think about the coordinates of the points we start with before the construction, and then each step in the construction gives us some new points with new coordinates, and this defines new numbers that we can use. Now it turns out that these new numbers we get will have very specific properties if we compare them to the numbers we started with. This is basically what this key result here is saying, which we'll be proving in this video and then using to show that these construction problems are impossible. So it says that if a specific number is constructible, in our case from like a point that has coordinate 0, 0 and a point that has coordinate 0, 1, then this field extension, so Q, where we adjoin this new number alpha over Q, has a specific degree. Namely, it has to have a degree which is a power of 2. So at the moment, I don't expect you to understand what this result says. We'll be explaining this in a lot of detail in the video. But basically what it's saying is that the numbers we can obtain from such a construction have certain algebraic properties, and therefore, if we have numbers that don't have these properties, then it's impossible to get them via such a construction. Okay, so this will dictate the course of the video. So the first thing we'll do is we'll establish the necessary theory in algebra in order to be able to understand what this key result says and be able to prove it. Then we'll be showing how geometric constructions using ruler and compass relate to this algebraic theory. And then in the final part, we'll be using this key result to prove that these three construction problems are impossible. In order to follow along, you don't really need to know any Euclidean geometry besides what I presented here in the start. You will need to know a bit of abstract algebra, namely what a field is, and also what a vector space is, and some of the properties of vector spaces, and some properties of polynomials. But aside from that, we'll be able to prove the impossibility of these last two construction problems completely from more or less from scratch. While in the first case, we need to use the fact that pi is a so-called transcendental number, which can be proved but is very involved. And so we'll take that result on faith, and then we can also prove the first point here. All right, so let's get started on the algebraic part then. So first we'll need to establish a bunch of definitions that we'll work with for the rest of the video. The first thing we'll need is what's called a field extension, which is basically just a larger field containing a given smaller field. So we suppose that K is some field that we have given. Then any field F which contains the field K is called a extension of K. And this we denote by F colon K, which we pronounce F over K. So if you want to think about this visually, you can visualize the larger field F as sitting above the smaller field K. Or another way to remember this nomenclature is to think about the larger field F as extending the smaller field K. So we're basically adding new elements to K to get a larger field F. For instance, you could think about the real numbers extending the rational numbers. Now, one reason this idea of field extensions is useful is because it allows us to associate a number to any field extension called the degree of that extension. So whenever we have a field extension F over K, then the larger field F can be viewed as a vector space over the smaller field K. Remember that in order to have some vector space over a given field K, all we need to be able to do is multiply each element of the vector space by elements in K, and well, we also need to be able to add elements in the vector space. But now, because F here is a field, we have an addition, namely the addition F, and moreover, we can define the scalar multiplication with elements of K to be just multiplications in F. And the reason that this works is that, well, the elements of K are a subset of F. So basically, scalar multiplication is just multiplication in F with the elements of K. So viewing F as a vector space over K really doesn't add any structure. In fact, it sort of forgets that we can also multiply elements of F with themselves, even if they don't lie in K. But what it does give us is that we can use all the concept from linear algebra to think about f. In particular, because f is now a vector space over k, it has a specific dimension, which is the dimension of f as a k vector space, and this will be called the degree of the field extension f over k. And we denote this degree of the field extension just by deg of f colon k. Now, of course, this dimension here of f as a k vector space critically depends on what field k we choose. So this degree here will also, well, depend on both f and k in the extension. To make sure these concepts are absolutely clear, let me give an example. So let's think of k as being the reals, and let's think of f as being the complex numbers. And then, well, the complex numbers are a field extension over the reals. This is just because, well, the real numbers are a subset of the complex numbers, and both of them are fields. Now, we can ask what the degree of this extension is. So the thing we need to do is we need to consider the complex numbers as being a vector space over the reals. So we think of the complex numbers as a real vector space. All this means is that we think of addition of the complex numbers as being addition of the vectors, and then scalar multiplication, we're basically just thinking about multiplying any complex number with a real number, and we just perform this multiplication in the complex numbers. So whenever we have some real number and we have some given, let's say, complex number, then we can just multiply r times c as complex numbers, and that defines the scalar multiplication. Okay, so now we want to think about what the degree of this field extension is. Well, by definition, the degree is just the dimension of the complex numbers as a real vector space. And, well, the dimension of the complex numbers as a real vector space is 2. Why is this? Well, one basis for the complex numbers as a real vector space is just the number 1 and I. Now, basically, by definition, any complex number can be expressed as, well, some real multiple of 1 plus some real multiple of I. That's how one usually defines complex numbers. And these two numbers are also linearly independent because I is not a real number. Okay, so in summary, because we know that the dimension of the complex numbers as a real vector space is 2, this is in particular also the degree of this field extension of the complex numbers over the reals. All right, so this brings us to our first proposition on field extensions, which is that the degrees of field extensions are multiplicative. So what do I mean? I mean that we now consider 3 fields. So in this case, we have a field G containing a field F, and this in turn contains a field K. So we have 3 fields which are related by containment. And now there are various ways to think about these 3 fields as field extensions of one another. So one way we can think about it is G being an extension of K. So that's what's happening here on the left-hand side of the equation. Or we could think about G as being an extension of F, or we could think about F as being an extension of K. And well, now it turns out that whenever we have a situation like this, the degree of the extension sort of on the outside here of G over K is equal to the degree of G over F times the degree of F over K. So I'm not going to prove this in full detail, but I'll just give the idea to show you what you would need to do. So the first thing we need to do is just gather all the information we have. So we know that the degree of G over F, this is just the dimension of G viewed as an F vector space. And now in a similar fashion, the degree of F over K is just the dimension of F viewed as a K vector space. So for the time being, let's assume that this dimension here is n, and that this dimension here is m. And now what we need to prove is that then the degree of G over K here is n times m. Okay, so what does it mean for the dimension of G as an F vector space to be n? Well, it means that we have a basis of n vectors which generate G as a vector space over F. So we have what we could call an F basis of vectors alpha 1 through alpha n for the vector space G. Now, in a similar fashion, the fact that the dimension of the vector space f over k is m means that we have a k basis, which I'll call beta 1 up to beta m for the vector space f. Now again, the thing we want to show is that the degree of the extension g over k is equal to n times m. So we want to show that this degree here, g over k, is equal to n times m. But by definition, this degree is just the dimension of g viewed as a k vector space. In other words, we need to somehow present in this case, a k basis containing n times m elements for g. And again, this has to be of size n times m, and that will prove the result. Okay, and well, now the answer to how to do this is the following claim, namely, if we consider the collection of alpha I times beta j, where I runs between 1 and n, and j runs between 1 and m, then this collection is in fact the desired k basis for g. So this is a k basis for g. So essentially we're just taking all products between the two different bases we have given. And well, this has size n times m, so the only thing we need to check is that this indeed forms a k basis for the vector space g. Now I won't be doing this, but essentially you just show that this is a basis in the usual way. So you have to check that this collection spans the vector space g using coefficients in k. And also you have to show that this collection here is linearly independent. And well, in order to do this, you just need to write out the definition for what it means for this collection to span and what it means for it to be linearly independent, and use the fact that these collections alpha and beta we had up here are bases for the corresponding vector spaces over either f or k. So to just briefly present the argument in words, if you take some arbitrary element of g, first you can express it as a linear combination of these alphas here using coefficients in f. And well, each of these coefficients that appears in this linear combination here will be in f, and therefore can be expressed as a linear combination of these betas here using only coefficients in k. So basically we just kind of break it down in two steps, and this will give you then a k-linear combination of these products here, of these basis vectors, which will express a arbitrary element in g. Then for the linear independence part, you just take an arbitrary k-linear combination of these new basis vectors, these alpha I times beta j's, and then you first interpret this linear combination as just a linear combination of the alphas over f, so with coefficients in f, because each of these betas here is in f, and each of the coefficients we had from k is in f, and from there you can then conclude that all those coefficients have to be 0, but in turn then you can use linear independence of these betas in the vector space f over k to show that, well, then also the coefficients in k which we originally had in their linear combination need to be 0. So basically it's just writing out the definitions and using the information we have. So if you want, you can write out a proof for this by yourself as an exercise, but I think it's not so interesting for me to go through all the formal details here. All right, so the next definition we'll need is that of a field generated by a specific element. Now it's possible to make a similar type of definition in far more generality, but for our purposes, we'll basically always just be looking at subfields of the complex numbers, and this will make our life easier, so I'll just give all the definitions in that restricted setting. So now we suppose in this restricted setting that the field K we're taking extensions of is actually a subfield of the complex numbers. And the reason this is a good thing to do is because the complex numbers are algebraically closed, which means that basically any polynomial we can come up with that has coefficients in this field K will factor in the complex numbers, which means that any such polynomial will have a root in the complex numbers. For now, though, we're just assuming that, well, this field K is a subfield of the complex numbers. And now we take some arbitrary element of the complex numbers, which I call alpha, and we want to think of the smallest field, which contains both this new element alpha and the original field K. So this thing will be called the field generated by the element alpha over K, and will be denoted like this. So it's K with round brackets with alpha inside. And again, this is the smallest field that contains both alpha and K. Well, the reason this thing exists is because, well, the complex numbers contain both alpha and K, so there is some field which contains both alpha and K, and we can just intersect all such fields, and this will give us the smallest such field, because the intersection of fields is again a field. Now, usually we'll be choosing alphas which are in the complex numbers but aren't already in K, in which case this field generated by alpha over K will be bigger, like strictly bigger than K. But of course it could be that this alpha here already lives in K, in which case, well, K is the smallest field that contains both alpha and K. So if alpha is actually already an element of the field K, then the field generated by alpha over K is just K itself. The next definition builds a relationship between field extensions and polynomials. So for this, we again suppose that K is some subfield of the complex numbers, and we suppose that alpha is some element of the complex numbers. We can now ask the question whether this complex number alpha here is the root of some polynomial which has coefficients in the field K. In other words, we can ask whether there exists a polynomial f in the polynomials over the field K, such that when we evaluate that polynomial in alpha, we get 0. Well, if there is such a polynomial, then we call alpha algebraic over the field K. So for example, let's consider K to be the rational numbers, and well, this is a subfield of the complex numbers. And then we could try different alphas. For example, alpha could be square root 2. This turns out to be algebraic over Q. So although square root 2 is not a rational number, we can square it and we get a rational number. So the polynomial x squared minus 2, if we substitute in square root 2 in here, we get 0. And this polynomial here has rational coefficients. So here the coefficient is 1, and well, the second constant coefficient here is 2. Those are both rational numbers. So we can define f to be this polynomial here, and well then f of alpha, so f of square root 2 is 0. So this shows that square root 2 is algebraic over Q. A similar thing would go for the imaginary unit I. If we square I, we get minus 1. So we could choose the polynomial g here to be x squared plus 1. And in that case, g of I is 0. So also the imaginary unit is algebraic over Q. On the other hand, there are numbers for which there exists no polynomial with coefficients in Q, such that they are a root of that polynomial. For instance, the number pi is such a number. We can never find a polynomial with coefficients in Q such that pi is a root of that polynomial. And this means that pi is not algebraic over Q, and we can express this by saying that pi is transcendental. Now, proving this is much more difficult than proving that some number is algebraic, because in order to show that a number is algebraic, you just need to find the right polynomial. On the other hand, to prove that a number is transcendental, you need to show that regardless which polynomial you would choose, it's not going to have the given number as a root, which is much harder. Okay, so now we know what it means for some complex number to be algebraic over some subfield K of the complex numbers. Again, this just means that there is some polynomial with coefficients in K such that the given number alpha is a root of that polynomial. Now, of course, whenever we have some polynomial that has alpha as a root, there'll be others which also have alpha as a root. For example, you could just multiply the polynomial with a given constant, which lies in K, And well, this will still have alpha as a root, because if you multiply 0 with a constant, you just get 0. So this means that whenever alpha is algebraic over k, there'll be actually infinitely many polynomials which have alpha as a root. But what this proposition here is saying is that we can sort of narrow this infinite collection of polynomials down to one canonical choice, which will be called the minimal polynomial of this number alpha. Okay, so this proposition is saying we have some alpha in the complex numbers, which is algebraic over k. And, well, if this is the case, so this means that there is a polynomial that has alpha as a root, then there exists some unique monic polynomial, which I'll call phi, which is a polynomial with coefficients in k. Moreover, this unique monic polynomial has alpha as a root. And moreover, if we choose any other polynomial, f, which has coefficients in k, which has alpha as a root, then this minimal polynomial phi here will divide f. And as I've already said, phi is called the minimal polynomial of alpha over k. And it's minimal in the sense of division, because whenever we have some other polynomial which has alpha as a root, then phi divides f. All right, so let's prove this. Now the reason this is true is basically just because we have a well-defined division algorithm for polynomials. So as a reminder of what this means, so this is just like the Euclidean algorithm for division of polynomials, or you could think of it as long division for polynomials. So if we're given some polynomials f and g, so these are polynomials with coefficients in k, and moreover we need to assume that, let's say the second polynomial here, g, is non-zero. Well, in that case, there exists some polynomial q and some polynomial r. So let's say there exists q and r. These are also polynomials with coefficients in k, such that the following equality holds, namely f is equal to g times q plus r, and moreover, the degree of r is going to be strictly less than the degree of g. Okay, so what are we doing here? Well, intuitively, we want to divide the polynomial f by the polynomial g. And this only works if g is non-zero, because we're not allowed to divide by 0. But provided g is non-zero, then we can always divide f by g, and what we get are two new polynomials, namely q and r. So q is basically the maximum number of times that g fits into f, and then r is the remainder from that division. And now if we've chosen the largest, well, q in terms of degree, such that g times q still fits into f, then the remainder will also have degree that is strictly less than g. So if this is perhaps a bit unfamiliar, we can just think about the same thing in terms of natural numbers. So exactly the same result holds for natural numbers. Whenever you have two numbers, f and g, and the latter one is non-zero, then you can find some q and some r, such that g times q plus r is equal to this original number. So intuitively, we're dividing f by g, and, well, g fits into f q times, but there might be some remainder here, but that remainder will always be strictly less than g, because if, well, it wasn't, then we could just increment q by another step. So the same idea works for polynomials, but instead of absolute magnitude, as we use for the natural numbers, we use the degree as sort of the measure of how large a polynomial is. All right, so now we're going to use this long division algorithm here to show that if alpha is algebraic over k, then it must have some minimal polynomial phi. So for this, we just define phi as the smallest degree polynomial that has alpha as a root and is monic. So we let phi be the monic polynomial of minimal degree that still has alpha as a root. So we know that there is some polynomial in k of x that has alpha as a root. And so we look at the collection of all of these polynomials and we just take one that has the smallest degree and is also monic. The reason we can assume that there's always also a monic one is that whenever we have some polynomial that has alpha as a root, then we can always multiply this polynomial by some constant c, and it'll still have alpha as a root. In particular, if this polynomial f here has some leading coefficient, let's call it a, we can multiply it by 1 over a, so divide out this leading coefficient and get a monic polynomial. So there'll always be some polynomial of minimal degree that is also monic. Okay, so now we've defined this phi, and what we need to show is that it'll divide any other polynomial that has alpha as a root, and moreover we need to show that it's unique. To show the first property, we suppose that f is some polynomial with coefficients in k, and moreover f should have alpha as a root. And I now realize that I was a bit imprecise when I defined what it means for a number to be algebraic. So I said that a number is algebraic if there exists some polynomial with coefficients in k that has alpha as a root, but in fact what I should have said is that there exists a non-zero polynomial with coefficients in k that has alpha as a root, because you could always choose the zero polynomial and that would have any number as its root trivially. But of course, that's not an interesting situation, so we want to choose a non-zero polynomial that has this alpha as a root. But now, okay, because the minimal polynomial is required to be monic, it in particular means that it's not going to be the zero polynomial, because it has to have a leading coefficient 1. So the definition for minimal polynomial is still fine, but what I should have said before in the definition of what it means for a number to be algebraic is that we want a non-zero polynomial in the polynomial ring over k, such that alpha is its root. In any case, we now want to show that phi divides f, and we use our above result to write f as phi times q plus r. And the reason we can do this is because phi is non-zero, because it's monic. And we also know that the degree here of r is going to be strictly less than the degree of phi. So we can write f like this. And now our goal will be to show that this remainder term is in fact 0. And the way we're going to do this is evaluate this polynomial at the point alpha. So then we know that if we plug in alpha to this polynomial f, we'll get 0. That's our assumption. But doing so, because we can rewrite f in this form, means we could also plug in alpha to each of these individual polynomials here and perform these operations and also get 0. So this needs to be equal to phi of alpha times q of alpha plus r of alpha. But now, by assumption, here this phi is some polynomial which has alpha as a root. So in fact, this term here is 0, so this entire part cancels. And what's now left over is that 0 is equal to r of alpha. Okay, so all of this implies that r of alpha is equal to 0, which means that, in fact, alpha is also a root of this remainder term r. However, we know that the degree of r here is going to be strictly less than the degree of phi. Now, by our choice of phi, we chose phi to be the monic polynomial, so in particular a non-zero polynomial, which is of minimal degree. So we know that it's not possible for r to be a non-zero polynomial, because otherwise phi would not be one of minimal degree. Hence, the only alternative is that r is in fact the zero polynomial. Otherwise, we would contradict the minimality of phi. And hence we conclude that r is in fact 0, and this means that this phi here divides the polynomial f by definition of what it means to divide a polynomial, namely that you can multiply phi times some other polynomial and get f. Okay, so phi in fact divides f. Okay, so the last thing we need to prove is uniqueness. And this basically follows out of the property we saw previously. So we suppose that psi is also some monic polynomial which has the same degree as this polynomial phi we found. So we suppose psi is monic and moreover, the degree of psi is equal to the degree of phi. Basically, now what I want to show is that phi needs to be equal to psi. Now, by the argument we had previously, we know that phi will divide psi, but also because psi is also a monic polynomial of minimal degree, so we could apply the same argument to psi to get that psi will divide phi. Now, if you write out exactly what this means, here this first relation means that we can obtain psi by multiplying phi by some polynomial f, and this other one says that we can obtain phi by multiplying psi with some polynomial g. So here f and g are just arbitrary polynomials. However, combining these two things here, we get that phi is actually equal to g times f times phi. And well, this puts some restrictions on what this g and this f can be, because in particular for polynomials we have that if we multiply polynomials of some degree, then the degrees add together. So the degrees of the polynomial phi here and of this multiplication have to be the same, and well, because we're just multiplying stuff here, it means that the degree of g times f has to be 0. So the degree here of g times f needs to be 0, which means that g and f both have to be constants, and moreover, this g times f has to be equal to 1. So in other words, what we've now determined is that in fact these multiples that we multiply phi by to get psi, and conversely we multiply psi by to get phi, are both constants, so they lie in the field K. So now the only question is, in order to show that psi is actually equal to phi, we need to show that in fact each of them needs to be equal to 1. And the reason why this follows is that both psi and phi were assumed to be monic. So we know that phi is monic, and we know that psi is monic, so if we would multiply psi by some constant which is not 1, then we would get a non-monic polynomial, which would contradict the fact that phi is monic. So therefore g has to be 1, and this shows then that phi is equal to psi. Okay, so with that we've proved all we need to show, namely that whenever we have some algebraic number alpha, which is algebraic over a field K, then there exists a unique monic polynomial which has alpha as that root, and that polynomial is minimal with respect to division, meaning that whenever we have some other polynomial which has alpha as a root, then that phi, this minimal polynomial, will divide that other polynomial f. Alright, so in the previous proposition we saw that whenever alpha is algebraic over some field K, then we have a minimal polynomial for alpha. And, well, we'd like to know in practice how to find this, and this is the content of the following corollary. So it says that whenever we have some polynomial with coefficients in K, which is monic and irreducible, and has alpha as a root, then f is in fact the minimal polynomial of alpha. So this basically just follows from the previous proposition, because whenever we have the minimal polynomial, it'll divide any other polynomial that has alpha as its root. So we suppose that f is such a polynomial, so we have it being a polynomial with coefficients in K. We suppose that it's monic and irreducible. So being irreducible, as a reminder, means that we can't write f as the product of two polynomials which have strictly positive degree. Or another way of saying this is that we can't factor f into two non-constant polynomials. And finally, we also assume that, well, alpha is a root of this polynomial f. Now we know by the previous proposition that the minimal polynomial phi will divide this f because alpha is a root of f. And what does this mean? Well, it just means that f can be expressed as the product of phi with some other polynomial g. But now, because f is irreducible, we know that it's impossible to write f as the product of two non-constant polynomials. And in particular, this minimal polynomial here is non-constant. So this implies, because f is irreducible, that g must in fact be constant. So g is an element of our field K. Okay, but now, by assumption, f is monic, And we also know that the minimal polynomial is monic, so g must in fact be 1. Otherwise, we would get a non-monic polynomial for f. So since f is monic, we get that g is in fact equal to 1, and hence the equality from before shows that f is equal to phi. Alright, so in summary, a concrete way to find the minimal polynomial for a given alpha is just to find an irreducible monic polynomial that has root alpha, and then by this corollary we're guaranteed that this is in fact the unique minimal polynomial. As an example of this, we can consider the following. So let's consider square root 2 as our alpha, and well, if we look at this element as being algebraic over the rational numbers q, then it has minimal polynomial x squared minus 2. The reason for this is that, well, on the one hand, if you plug in square root 2 into this polynomial, you get 0, and all the coefficients in this polynomial are rational numbers. So this shows that, well, this polynomial has square root 2 as a root. Moreover, this polynomial is monic because it has leading coefficient 1. And finally, it's irreducible because square root 2 is not a rational number. If you wanted to check directly that this is irreducible over q, you would do the following. You would say, okay, if I can factor this into two non-constant polynomials, they both have to be of degree 1. So we would have to have some ax plus b times some cx plus d that equals x squared minus 2. So that because of the degree 2-ness of this polynomial, there's only one way in which we can factor it into non-constant polynomials, namely this. And here I've just chosen arbitrary coefficients. But if you calculate what you get out here, you would get ac x squared plus bc plus ad times x plus b times d. And this needs to be equal to x squared minus 2. And from here you get several equations for the coefficients by comparing them across this equation. So we know from the leading coefficient here that needs to be 1, that a times c needs to be 1. So this all implies that a times c is equal to 1. There's no x term in this polynomial here, so b times c plus a times d needs to be 0. bc plus ad is equal to 0. And finally, we need that b times d is equal to minus 2. And now using these equations here, one can show that in fact it's not possible to find rational coefficients for any of these numbers that would satisfy these equations. Another way to think about this is because we're considering the rationals as a subfield of the complex numbers, we can just take the roots of this polynomial in the complex numbers and factor it. So in the complex numbers, this polynomial here factors as x minus square root 2 and x plus square root 2. And well, neither of these polynomials here of the factors are polynomials with rational coefficients because square root 2 is not a rational number. But basically, the same argument holds if you consider q to be some subfield of some other field than the complex numbers and you consider this polynomial here. It's still irreducible over q by this more general argument down here. Okay, so in fact, x squared minus 2 is then the minimal polynomial of square root 2 considered over the rational numbers. On the other hand, if we consider square root 2 over the reals, because square root 2 is itself a real number, and well, we can use this polynomial here instead, namely x minus square root 2. If we plug in square root 2 here, we get 0 again. This is a monic polynomial, and all its coefficients are in R. Therefore, this polynomial here is the minimal polynomial for square root 2 over the reals. So you can see that whatever the minimal polynomial is depends on which field you're considering it over. In particular, if you choose a larger field, so if I choose R instead of Q, the degree of the minimal polynomial might decrease. The reason for this is that, well, this polynomial here still has root square root 2, and you can consider this one as a polynomial with real coefficients, And well, then the minimal polynomial over the reals will divide this one, so it will have degree of at most 2. But as we see in this example, it can actually have degree strictly less than 2. All right, this brings us to the last proposition of this abstract algebra bit, which will reveal why we even care about these minimal polynomials. The reason is that the degree of a field extension for these simple field extensions where we just adjoin a single element will exactly correspond to the degree of the minimal polynomial of that element. So this gives us a concrete way of computing degrees of field extensions using minimal polynomials. So for this, we again assume the setting that our field K is a subfield of the complex numbers, and we assume that alpha is algebraic over K, which means that there exists some non-zero polynomial which has alpha as its root. Then this proposition says that the degree of the field extension of this field generated by alpha over K is equal to the degree of the minimal polynomial of alpha. Okay, so for the proof, we assume that alpha is some algebraic element over our field K, and we consider its minimal polynomial phi. So we let phi be the minimal polynomial of alpha over K. And now we'll be a bit more concrete about what phi is, so we'll give the coefficients in this polynomial some names. So let's call it x to the n plus a n minus 1 to x to the n minus 1 plus all the way down to a0. Now what we want to show is that the degree of this field extension here, of this field generated by alpha, is actually equal to the degree of phi, which in our case is n. So what do? Well, we need to write down a basis for this larger field generated by alpha. So what we're going to do is we're going to consider the collection given by alpha to the 0, so that's just 1, alpha, alpha squared, and so on, up to alpha to the n minus 1. The claim will be that this is actually going to be a basis for this field generated by alpha. So claim, so this forms a basis for K of alpha. Let's start by showing linear independence of this collection, viewed as a collection of basis vectors over K. So for this, we suppose that we have some linear combination of this collection that equals 0. So we'll call this beta 0 times 1, which is alpha to the 0, plus beta 1 times alpha, plus, and so on, up to beta n minus 1 times alpha to the n minus 1. And we're supposing that this is 0, and these beta I are elements of our field K. Now, if these beta I are not all 0, we can consider the polynomial that has these beta I as coefficients. So we consider f to be equal to beta 0 plus beta 1x plus, and so on, up to beta n minus 1 to the x to the n minus 1. So this is now a non-zero polynomial because at least one of the coefficients is not 0. However, if we substitute alpha into this polynomial, so what do we get? We get beta 0 plus beta 1 alpha plus, and so on, up to beta n minus 1 alpha to the n minus 1. And we assume that this is 0. Okay, so we've now shown that f is a non-zero polynomial that has alpha as a root. But on the other hand, this polynomial f is of degree n minus 1, whereas the minimal polynomial had degree n. Now we know that the minimal polynomial is the polynomial with minimal degree, so in fact this is impossible. Otherwise it would contradict minimality of our minimal polynomial, and therefore all of the beta coefficients are 0, and this shows that this collection here is linearly independent. The second thing we need to show is that this collection actually spans K of alpha, and we'll do this in 2 steps. In the first step, we'll show that K of alpha can actually be represented in the following more concrete way, namely, so I'll write this as K of square brackets alpha, and this is just polynomial combinations with alpha as the unknown variable. So this is sums of the following form. So we have some beta I times alpha to the I, and I ranges from 0 to m, where m is some arbitrary natural number, and the beta i's all lie in the field K. So one of these inclusions should be clear because, well, K of alpha here is a field that contains both the elements of K and also alpha. And here what we have are just, well, polynomial combinations of alpha. So basically we're just combining elements of K and alpha using field operations. So we're multiplying them and adding them up. And so the result should again be in this field K of alpha. The other inclusion is a bit more tricky. So we want to show that this field generated by alpha is actually contained in these polynomial combinations of alpha. And the way we're going to do this is we're going to use the fact that by definition here K of alpha is the smallest field which contains alpha and K. And well, if we could show that this K with the square brackets alpha, so these polynomial combinations actually form a field that, well, contains alpha and K, then we would get the inclusion in the desired direction. So first off, we can observe that K square brackets alpha here actually contains alpha and all elements of K. Why is this? Well, to get the elements of K, you just set all the coefficients to be 0 except the constant coefficient beta 0, and you can set that to be anything in K, and that gives you all the elements of K. And well, to get alpha, what you need to do is you just set every coefficient beta I to be 0 except for beta 1, which you set to be 1, and then you get alpha. So this thing certainly contains K and alpha, but the tricky part is to show that this is actually a field. Now, in order to show that this is a field, we need to show that, well, it's closed under addition, under additive inverses, and under multiplication and taking multiplicative inverses. Now, the way you add and subtract elements here is just like you do with polynomials, and we know that polynomials form a ring, so you can add and subtract polynomials, so they have additive inverses. You just take all the coefficients with a minus sign, and then if you add those to the original polynomial, you get 0. You can multiply these types of polynomial combinations and again get such a polynomial combination just by using the rule for polynomial multiplication. So really the only tricky bit is to show that we actually have multiplicative inverses that are also of this form for any such element. Now, unfortunately, I wasn't able to find like a nice concrete way of writing down what the multiplicative elements are. Instead, I'll have to appeal to another theorem in order to show you that they exist. So the theorem we'll be using is called Bézout's identity. In the case of polynomials, it says the following. So we let f and g be some polynomials over a field K. And moreover, we assume that their greatest common divisor is some polynomial d. Well, then the theorem says that there exists two more polynomials, r and s, again, elements of this polynomial ring over the field K, such that if we multiply r with f and add to this the multiplication of s times g, then this is equal to d. So in other words, we can always, for any two polynomials, find multiples of each such that if we take the sum of them, we get back the greatest common divisor of them. In particular, if these two polynomials here are coprime, which means that the greatest common divisor is 1, then we can find like a combination of this form that gives us 1. Now, the proof of this theorem isn't particularly difficult, but I really don't want to do it here. If you want, you can go look it up, for example, on Wikipedia or in any algebra book. The same thing also holds for integers, and it's maybe a bit simpler to think about in that context, but in general, whenever you have a so-called principal ideal domain, you can certainly apply this theorem. Now, in our case, we're going to apply this theorem to some element that we have here, some polynomial combination of the alphas, together with with phi the minimal polynomial of alpha. So what we do is we take some f in k of alpha, and maybe I'll denote this f bar because what we want to do is now think about this as an abstract polynomial with unknown x. So we're going to consider f in k of x, which is basically the same polynomial, just that we've replaced the alphas here with unknown x. Or another way of saying it is that f here is an abstract polynomial in the polynomial ring over the field k, where we've taken the same coefficients beta I as we had in this original element, which was a polynomial combination of the alphas. So it's just some polynomial such that f of alpha is equal to f bar. Now what we're going to do is we're going to apply this Bézout's identity to this polynomial f and phi. Now because phi is irreducible, so we've shown that any monic irreducible polynomial with root alpha is the minimal polynomial, so in particular the minimal polynomial is irreducible. This means that the GCD of phi and f will be 1. So phi and f can't have any common divisor aside from 1, because otherwise we would be able to factor phi. So this means that we can find some polynomials r and s such that r times f plus s times phi is equal to 1. So now we've used Bézout's identity, and I can now erase the statement to make some more space. Now what we're going to do is we're going to evaluate this expression here, which we obtained at alpha. So if we evaluate the right-hand side at alpha, well, this is just a constant polynomial, so we get 1. But if we evaluate the left-hand side at alpha, we plug in alpha to each of the polynomials occurring here. So this implies that r of alpha times f of alpha plus s of alpha times phi of alpha is equal to 1. But we know by definition that if we evaluate the minimal polynomial at alpha, this is 0, so these terms cancel. And this shows then that r of alpha times f of alpha is equal to 1. But f of alpha is just f bar by the way we've constructed f. Therefore, we've shown that we can always find for any f bar that is some polynomial combination of the alphas here, we can always find some polynomial r such that if we evaluate it at alpha and multiply it by f of alpha, which was our f bar, we get back 1. So this r of alpha is the multiplicative inverse to f bar, and yeah, we've shown that in general this always exists. Of course, this should only work if f bar is non-zero. So what happens if f bar is 0? Well, in the case when f bar is 0, what we would get is that f would be the 0 polynomial, and in that case the GCD of 0 with phi would no longer be 1. Instead, because anything divides 0, the GCD of phi with 0 would again be phi, and this argument wouldn't work in the same way. You'd just get that you'd find polynomials r and s such that r times f plus s times phi is equal to phi, and then if you evaluate at alpha, well, the right-hand side now is no longer a constant 1, it's phi, so you'd get 0 on the right-hand side, and so what you'd get then is that r of alpha times f of alpha is 0, and this would not be a contradiction. It's just again restating that, well, f of alpha is 0. Okay, so in summary, we've shown that this collection here of these polynomial combinations of alpha is actually closed under all the field operations, and therefore it is a field. And because it contains alpha and k, and well, k of alpha is the smallest such field, we actually also have the inclusion in the other direction, which proves this equality I've claimed here. Okay, so in this first step, we've sort of reduced the problem a bit because we've shown that, well, this sort of abstract-looking field here generated by alpha can actually be represented in a fairly concrete way, namely in polynomial combinations of alpha. And well, now in the second step, we need to show that this collection here is actually enough to span all of these polynomial combinations. So the way this is going to work is that we're going to use the minimal polynomial relation here in order to be able to reduce degrees of alpha that are greater or equal to n. So if you plug in alpha into this equality here of that describes the minimal polynomial, what you get is that 0 is equal to alpha to the n plus a n minus 1 alpha to the n minus 1 plus and so on all the way up to a0. And well, you can rearrange this equality to get that alpha to the n is equal to minus a n minus 1 alpha to the n minus 1 minus and so on up to minus a0. So I've just moved all of the stuff here that wasn't alpha to the n to the other side of the equation. Now it doesn't matter too much what the coefficients here are. The point is that we can express alpha to the n as a polynomial combination of alpha that has degree n minus 1. In particular, whenever we have alpha to some power which is greater or equal to n, we can always use this relation here to reduce the degree by 1. In particular, this means that in fact this set of polynomial combinations in alpha here actually can be written in the following way. So we only require polynomial combinations up to degree n minus 1. So here we no longer have an arbitrary degree of the polynomial combination. We have a fixed degree, namely n minus 1. And again, these coefficients beta I are in k. And the reason for this equality here, I mean, these types are clearly included in this type because the above type is more general. But the reverse inclusion holds because we can always take a polynomial combination of this form and then use this relation iteratively to reduce the degree by 1 until we reach the point where we can no longer apply this relation, at which point the maximal degree will be of degree n minus 1, because we can always apply this as long as the degree is greater or equal to n. Of course, these coefficients here don't have to be the same once we perform the reduction. I've just used the same letter here because they're just varying in k. In fact, you can use this relation to explicitly calculate how you would reduce like a higher degree polynomial to a lower one, but it'll be a huge mess because of all of the coefficients that crop up there. All right, so now we've actually accomplished proving that this collection here spans k of alpha. Why is that? Well, we've shown in the first step that this field generated by alpha is actually equal to arbitrary polynomial combinations of alpha. But then we used the relation given us by the minimal polynomial to show that this is actually the same as if we just only consider polynomial combinations up to degree n minus 1. And well, these types of polynomial combinations are precisely linear combinations of these elements. Therefore, any element in k of alpha can be written as a linear combination of these monomials of up to degree n minus 1, and this shows that this collection spans k of alpha. So in summary, we've shown that this collection is indeed a basis for k of alpha, and because it has n elements, and n was the degree of the minimal polynomial of alpha, we have shown that the degree of this field extension k of alpha over k is equal to the degree of the minimal polynomial, which was what we wanted to show. All right, so that concludes all of the abstract algebra that we'll be needing. So next we'll turn to relate the geometric notion of constructibility of a point to some sort of algebraic properties of the coordinates of those points that we can construct. This is what's stated in the following proposition. So here we're assuming that we're working in R2, so all the points we consider will have real coordinates. So we suppose that we have some point, P, which has coordinates alpha, beta, which can be constructed from some given set of points P1 through Pn, which each have coordinates A1, B1, and so on. And well, we want to use ruler and compass and the rules I presented in the beginning of the video to construct this point P here. So if this can be done, then these coordinates alpha and beta of this constructed point can be obtained from the coordinates of the original points we started with, P1 through Pn, by repeatedly using field operations, so that's addition, subtraction, multiplication, and division, along with taking square roots. So this gives us a way of relating these constructed coordinates here, alpha and beta, to the coordinates we started with. It's just saying that they can be sort of calculated from the existing coordinates using field operations and square roots. For the proof, we need to show that whenever we apply the rules of construction, so either creating a line between 2 points or creating a circle, then the new points we get by doing this, so intersection of these lines or circles, can be expressed, so the coordinates can be expressed from the original coordinates using field operations and square roots. So the first thing we need to do is describe lines and circles using coordinates. So for the lines, suppose we're given 2 points in the coordinate system like this. So we're given some point, let's say A2, B2, and some point down here, A1, B1. And now we've drawn a line through these points. Well, then the equation for this line is as follows. It's y minus b1 is equal to b2 minus b1 divided by a2 minus a1 times x minus a1, like so. So one way to think about how you would obtain this formula is to think about translating this line here so that it intersects with the origin, and then you just apply the slope formula for a line. So that's y is equal to the slope times x plus the intercept, but in this case the intercept would be 0 for the translated line, so this translated line just has formula y is equal to the slope times x, and this term here is the slope because we're just taking the difference in y coordinate and dividing it by the difference in x coordinate. And well, then we've obtained the equation for this translated line, and well, then we can just translate the line back by shifting, well, the line by this coordinate here, and that gives you this equation. So you see we've shifted y by b1 and x by a1. In a similar way, we can obtain the equation for circles. So here again we have some point a1, b1. That'll be the center point of our circle, and then we have some other point a2, b2, which will be the point determining the radius. And now if we draw a circle, we can express all the points on the circle as follows. So we know the equation for a circle is that we want x minus a1 squared plus y minus b1 squared. So again, you can think about this as sort of centering the circle at the origin. We want this to be equal to r squared. But the radius is just the distance between these 2 points here. So we can actually calculate it to be a2 minus a1 squared plus b2 minus b1 squared. So here we get an equation for all the points on this circle. So they have to have coordinates x and y such that this equation here holds. And the only other parts of the equation involve the coordinates of the points we're given. Okay, so now that we've written down the equations for lines and circles, what really interests us is what happens if we intersect lines and circles that we obtain from using the methods we're allowed to use in the construction. So the first thing we'll consider is what happens if we intersect a line with a line. Let's say we have 2 lines, one here and some other line here. Now suppose that the equation for the pink line is y is equal to m1 x plus q1, and the equation for the orange line is y is equal to m2 x plus q2. And notice that by this equation up here, both m and q for both of these lines can be expressed in terms of the original coordinates of the points we use to construct a line using field operations. Alright, so now to get the intersection point here between these 2 lines, we need to equate both of their equations here and solve for x or y. So doing so here gives that m1 x plus q1 is equal to m2 x plus q2. And well, this then implies that x is equal to q2 minus q1 divided by m1 minus m2. So as I noted before, we can express q2, q1, m1, and m2 all as some field operations of the coordinates of the points we drew these two lines through. And now we're again just using field operations to solve for x. So this means that the x-coordinate of this intersection point can also be expressed from the coordinates of the original points we had using just field operations. Okay, so maybe let's call this xi for intersect. And well, we get yi by just substituting this xi into either one of the equations for the line. So we could write it, for example, as m1 times xi plus q1. And here again we see that we can obtain yi by just using field operations on the coordinates of the original points we drew the lines through, because again m1 can be expressed using field operations from those coordinates and q1 can. And we also now know that xi can also be expressed using field operations. So it's a bit complicated if you would write out the entire formulas for this, but we're just using field operations on the coordinates we started with to draw the lines. Okay, so this shows that at least for two lines, when we intersect them, we can express the intersection point from the coordinates of the points we started with using only field operations. Now the second case we need to examine is what happens when we intersect a circle with a line. So here we have some line, and then we have some circle which intersects it. Now the equation for the line is y is equal to mx plus q. And the equation for the circle is x minus a1 squared plus y minus b1 squared is equal to r squared, where r squared is, well, this quantity here. So we know we can express r in terms of the coordinates defining the circle using field operations. Okay, so now we want to again solve both of these equations, so we can just plug in this top equation here for y in the bottom. So I'll do this briefly. So x minus a1 squared plus, now we have mx plus q minus b1, the entire thing squared, is equal to r squared. And what you now see is that if you multiply out these brackets here, what you get is some quadratic equation in x. So this thing here is equal to some capital AX squared plus bx plus c, and this is equal to r squared. And these capital A, capital B, and capital C are some multiples of these quantities that appear here. So in particular, they can also be written using just field operations based on the coordinates we started with. So we can now solve this equation using the usual quadratic formula. And well, if you think back to what the quadratic formula does, it just takes some square root of some quantity, then adds something to it and divides by something. So this means that x1 and 2 can be obtained from the existing coordinates we started with, or I'll just maybe call existing quantities, using the field operations plus square roots. Now, because in the geometry these intersection points, we're assuming them to exist, the quadratic formula will actually yield real number results and not complex number results. And again, because all of these quantities that appear here in this quadratic equation can be expressed from the existing coordinates using field operations, it means that also in the solution formula for the quadratic equation we'll have just using field operations plus the additional square root that crops up there. Now the last case we need to consider is the intersection of two circles. And for this I'll erase this to make a bit more space. So here we have some two circles that were given by some construction, and we now want to calculate their intersection points. So here the orange circle can be described as x minus a1 squared plus y minus b1 squared is equal to r1 squared. And the pink circle can be described as x minus a2 squared plus y minus b2 squared is equal to r2 squared. Again, all the quantities that aren't unknown can be expressed from the existing coordinates using field operations. Now we solve these equations simultaneously again. So one way to do this is we can subtract the first from the second, and this will cause all of the x squares and y squares to cancel out. So here, if we expand this, we would get an x squared. Down here, we'd also get an x squared, and if we subtract these from one another, we cancel out the x and the y squares. So we have some linear equation in x and y that is equal to, say, r1 squared minus r2 squared. We can then solve this linear equation for, say, x, and this can be done using only field operations. For example, we saw that this works up here. Therefore, we can express x coordinate, for example, using only field operations and the existing coordinates we started with. Then to get the y coordinate, we can use one of the existing circle equations and plug it back in. This gives us like some quadratic equation in y, which we can then again solve using the quadratic formula. And this will involve, again, only field operations on existing coordinates along with square roots. Okay, so what we've done is we've shown that whenever we have lines or circles drawn through existing points with known coordinates, their intersections, so lines with lines, circles with lines, or circles with circles, can be obtained from these existing coordinates that we know using only field operation and taking square roots, which is what the proposition claimed. And we can just always iterate this throughout the construction, so we can compute any new intersection points we obtained using just field operations and square roots. Now, the corollary of this previous proposition, which we'll be using in order to show that certain construction problems are impossible, is the following. So if we have some point P, again with coordinates alpha and beta, that can be constructed from the point 0, 0 and 0, 1, then, well, we can obtain alpha and beta from the coordinates 0 and 1, which are just the coordinates that we have started with, by repeatedly applying field operations and square roots. So that's just specializing the previous proposition to the case where we start with these two given points. Now the new bit is that we're going to relate this to some algebra using fields in the following way. So if alpha and beta can be obtained from the points 0, 1 by repeatedly applying these field operations and square roots, what this means, or one way of expressing what this means, is saying that there is going to be some tower of fields, which is basically just like an inclusion of a field f0 into f1 into f2 and so on up to fk. So here f0 is the rational numbers. This is included in some field f1, this is included in some field f2 and so on up to some field fk. And moreover, this point alpha will be an element of this largest field fk, and each of the fi's is obtained from the previous field by adjoining some square root. Okay, so why does this tower of fields exist? Well, you just think about constructing numbers by iteratively applying these operations. So if you start with 0 and 1, and you apply any number of field operations, you basically end in the rational numbers Q, because the rational numbers are the smallest field that contains the points 0 and 1. And then anytime in the procedure you need to calculate a square root, you basically just add that square root to the existing field if it isn't already there. So let's say in our process of calculating the coordinates for alpha and beta, we need to use square root 2 or something like that. Then we would just add square root 2 to Q by adjoining it. So we consider the field generated by square root 2 over Q. And this then gives us a larger field f1, which contains square root 2 and Q, and it's the smallest field that does. Basically there we can again perform all the field operations we want, and at some point we might again need to take a square root. And well, if that square root doesn't already exist in f1, for example, it could be square root 3, which wouldn't exist in Q adjoin square root 2, we would just add square root 3 to get a larger field f2. And we can basically proceed in that way, and this sort of tracks how we calculate these coordinates alpha and beta from the existing coordinates 0 and 1. So in the end, alpha will be an element of this largest field fk, which we obtain after finitely many steps of applying field operations and square roots. So we only sort of advance in this tower every time we take a square root that doesn't already exist in our field. But in any case, the point alpha will be in fk, and well, the only things we've done to advance in this tower is add square roots, so that's what this part here is saying. Now the reason this way of expressing what's happening here when we're performing these operations on the coordinates that we have already given, the reason this is useful is because the degree of this field extension, so the fk over q, will be a power of 2. Why is this? Well, each time we adjoin a square root, either the square root is already in the field, in which case we're adjoining an element which is already in the field and that does nothing. So the degree of the extension fi over fi minus 1 could be in principle 1 if this square root already exists in fi minus 1. Or in the case where it doesn't exist, it'll be an extension of degree 2, because adjoining a square root, well, a square root always has a minimal polynomial of degree 2. So you can just take x squared minus this element you're adjoining the square root of, and that will be the minimal polynomial of this square root. So each step here in this tower, so like f1 over f0 has degree 2 or 1, then f2 over f1 will have degree 2 or 1, and f3 over f2 will have degree 2 or 1, and so on. So each of these steps has degree either 1 or 2. And then using the proposition we had, which said that the degrees for extensions multiply, we can apply this proposition like k times to get that fk over f0, which was q, needs to be like the multiple of all of these intermediate degrees. And since all of those intermediate degrees were powers of 2, so either 2 or 1, we get that this big extension fk over q will also be a power of 2. Okay, so maybe this is a bit complicated, but I'll summarize again. So whenever we have a point with coordinates alpha and beta, and we can construct it from starting point 0, 0, and 0, 1, well, then we can obtain the coordinates of this point, so alpha and beta, by repeatedly applying field operations and taking square roots, which is the same thing as saying that there is some tower of fields of this following form, where each of the fields in the tower can be obtained from the previous one by adjoining square roots. And as a consequence of this, the degree of fk over q will then be a power of 2. Now, the previous result is almost what we need in order to be able to show the non-constructibility results we want. However, we need to refine it slightly in the following corollary. So the corollary says that if alpha is constructible, so it's some coordinate that we can construct, then the field generated by alpha over q has degree 2 to the power k for some arbitrary integer k. So this is almost the same as the proposition from before, but instead of considering this tower of fields and so on, where the largest one is fk, we're directly considering the field generated by alpha over q. So to prove this, we note the following. So by the previous proposition, we have that alpha is contained in fk, which is that field we got through this tower of fields where we repeatedly adjoin square roots. And we also know that the degree of fk over q is some power of 2. So it's like 2 to the, let's say, m for m in the natural numbers. Okay, so now fk is some field which contains alpha, and it also contains all the rational numbers, because any field of characteristic 0 has to contain the rational numbers. Or another way you could see it is that in this tower we constructed previously, like q was the smallest field in that tower, so it's contained in fk. So in any case, fk is a field that contains alpha and q, which means that in particular it contains the field generated by alpha over q. So since, well, alpha is in fk and q is a subset of fk, this implies that the field generated by alpha over q is a subset of fk. So thus we have the situation where q is contained in this q of alpha, and this is contained in fk. We now apply the proposition on the multiplicativity of degrees for these types of towers of fields for the last time. Namely, we know that the degree of q of alpha over q times the degree of fk over q of alpha needs to be equal to the degree of fk over q, which by assumption is 2 to the m. So now what we have is that, well, the degree of q of alpha over q, that's the thing we're interested in, times some natural number is 2 to the m. So the only possibility is that, in fact, both of these numbers here are also powers of 2, just by thinking about prime factorizations. So this implies that the degree of q of alpha over q is equal to 2 to the k for some k that is less than or equal to m. And, well, this is exactly what we've claimed in the corollary. All right, so this corollary is the key result I started the video with. It's saying that if we can construct some coordinate, then we can consider the field generated by that coordinate over the rational numbers, and this will necessarily have a degree of power 2. Therefore, if we think about the contrapositive to this statement, if we have some coordinate alpha, and we consider the field extension q of alpha over q, and this does not have degree of power 2, then it cannot be that alpha is constructible. And that's exactly what we'll be using to show the non-constructibility of those three problems that we're interested in. Okay, so we've now reached the point where we can finally prove what we started out to prove, namely the impossibility of constructing certain figures, and the first one is that it's impossible to square the circle. So for this we're going to consider the unit circle, and we can suppose that we've drawn this circle basically based on the origin and the point 0, 1. Now by the formula for the area of a circle, which is pi r squared, this circle has area pi. Now suppose that we could somehow construct a square with area pi, well then the length of this segment here would be square root pi. Now in Euclidean geometry it's always possible to transfer the length of a given segment, so for example this segment here, to a given line. In particular, we could transfer this segment here to this line which defines the y-coordinate axis, and this would mean that we would be able to construct a segment here which has length square root pi, so we would be able to construct the coordinate 0 square root pi. So this means that if we can square the unit circle, well then the number square root pi is constructible. And well then by our key result, this would imply that the degree of the field generated by square root pi over q would be some power of 2. However, this is not possible since pi is transcendental. I'll elaborate on this, but we need to use the fact, which I won't prove, that pi is transcendental over q. So transcendental, this just means it's not algebraic. So in particular, this also means that square root pi is transcendental over q. Because if we had some non-zero polynomial with rational coefficients that had square root pi as a root, we could just square all of the unknowns and get a polynomial that had pi as a root that also has rational coefficients. Okay, so this implication is not the fact. The fact is that pi is transcendental over q, but this then implies the the fact that also square root pi is transcendental over q. We're now going to use the fact that square root pi is transcendental over q to show that the degree of square root pi, so the field generated by square root pi over q, has to be infinite. So the claim that we're going to show is that the degree of the field generated by square root pi over q, or in fact the degree of any field generated by a transcendental number, is going to be infinite. And well, the reason for this is that if you consider powers of square root pi, so we can consider the collection 1 square root pi squared, square root pi to the 3, and so on, all the way up to any arbitrary power of square root pi, so to the m. So this is some arbitrary collection of monomials in square root pi. So this is linearly independent over q for all natural numbers m. So regardless how large we choose m, this collection here is linearly independent, which means that whenever we would have like a basis of this vector space here over q, it has to have dimension greater than m for any m in the natural numbers, which means that its dimension has to be infinite. Okay, so why is this collection here linearly independent over q? Well, it's basically the same argument we used when we proved that the collection of these alphas for some algebraic number alpha is linearly independent. So suppose not. Well, then we would have some rational numbers qi and q such that, you know, q0 times 1 plus q1 times square root pi plus and so on up to qm times square root pi to the m is equal to 0, and the qi's are not all 0. So this would be what it means for this collection to be linearly dependent for some m. Okay, but then consider just the polynomial that has these qi's as coefficients. So we consider, I don't know, f equal the sum of the qi to the xi, where I runs from 0 to m. Now this is a polynomial that when you evaluate it at square root pi gives you 0, and it has rational coefficients, and so this would show that square root pi is algebraic. But in fact, square root pi is not algebraic, so we cannot have such a relation here where not all of the coefficients are 0. Okay, so the existence of such a polynomial would contradict the transcendentalness of square root pi. Therefore, in fact, this q adjoined square root pi is an infinite dimensional vector space over q, and so the degree of this extension is infinite. In particular, it's not some power of 2, and therefore square root pi cannot be constructible. Okay, so that proves that it's impossible to square the circle, assuming that we accept the fact that pi is a transcendental number, which can be proved, but is pretty involved. Now for the remaining two problems, namely doubling the cube and trisecting the angle, I can actually give complete proofs which don't assume any facts like pi being transcendental, and we'll use the theory we've established so far. So for squaring the cube, we'll again assume the same setup we had before. So we assume we're given points 0, 1 and the origin 0, 0, and we consider the unit cube, which isn't really strictly speaking a part of the Euclidean plane, but you just think about a line segment and sort of the cube sitting on there, and yeah. So this thing has volume 1, and we now want to double this volume. So we somehow want to construct a cube that has volume 2. Specifically, we don't want to construct the entire cube, we just want to construct, you know, one of these segments, which then, if you cube the segment, you would get 2. But this is just sort of a geometric way of expressing that we want to construct a third root of 2. So, as I said, in that case, this segment here would have to have length a third root of 2. And again, by the fact that we can always transfer length of line segments to existing lines, we could then extend here along the y-axis and get the length of this line segment there, and that would then give us a coordinate 0 third root of 2. And so if we could perform this construction, it would mean that this number here, the third root of 2, would be constructible. So if doubling the cube were possible, so if it were possible, then this would mean that the third root of 2 would be constructible. And well, then by our result, the degree of the field generated by the third root of 2 over q would be some power of 2. So to show that this is not the case, we'll show that the degree of this field extension here is in fact 3, so it's not a power of 2, and this will allow us to conclude that such a construction is impossible. Okay, so the claim we'll use here is that in fact the degree of the field extension we're interested in is in fact 3. And to prove this, we'll show what the minimal polynomial of the third root of 2 is, and we'll show that it has degree 3. So maybe I can just write this here, because if we consider the polynomial x to the 3 minus 2, so this is the minimal polynomial of the third root of 2 over q. So we showed in the algebraic part that whenever we have a minimal polynomial for some algebraic number, then the degree of the field extension where we adjoin that number is just the degree of the minimal polynomial. And moreover, we also showed that whenever we have a monic irreducible polynomial that has our given number as a root, then it's going to be the minimal polynomial. So this polynomial here is already monic. So all we need to show is that it is irreducible over q, and then we'll have proved that this is the minimal polynomial of the third root of 2. So what we need to show is that this polynomial here is irreducible over the rational numbers. To prove this, we'll proceed by contradiction. So suppose that this polynomial here would factor. So in this case, x to the third minus 2 would be equal to the product of a polynomial of degree 2 with a polynomial of degree 1. So the form would be x squared plus, let's say, ax plus b times x plus c. Now the reason we can assume that each of these polynomials is monic is because if we multiply these two parts, we have to get coefficient 1 there. So in principle, I mean, you could have two coefficients here which cancel each other out, but then we can just divide like each of them by those coefficients to get monic polynomials. So there's not really any loss of generality if we assume this. Now if you look at this equation here, if you plug in minus c into this equation, you get 0 because this part here becomes 0. So this means that minus c to the third power minus 2 is equal to 0. Or in other words, minus c to the third is equal to 2. Now moreover, because c is some rational number, so we're assuming that this is reducible over q for the sake of contradiction, so this means that all of these coefficients here have to be rational numbers. We can write c as the quotient of two integers. So we set c to be, let's say, c1 by c2, and to get rid of the annoying minus sign and just set minus c to be c1 over c2. And c1 here and c2 are integers, so it doesn't really matter if we have a minus or a plus. We would just choose different c1s and c2s. Okay, so this implies that c1 divided by c2 to the power 3 is equal to 2. And well, this implies that c1 to the third is equal to 2 times c2 to the third. All right, so this means that c1 to the third is even because it's 2 times some other number, but because we're just taking products of c1, it means that 2 also has to be a factor of c1 itself, so this means that c1 is even. So we conclude that c1 is even. Well, in this case, we can write c1 as 2 times, let's say, r, and well, this then implies that, well, c1 to the third is equal 2 to the power 3 times r to the power 3, and we know that this is equal to 2 times c2 to the power 3. And well, now we can cancel one of the 2's here, so we get that c2 to the third is 2 to the power 2 times r to the power 3, but by the same argument as before, this means that c2 is actually even. So now to convert this into a contradiction, we could have, at this point here, when we defined c1 and c2, we could have assumed that they don't have any factors in common, because otherwise we could have cancelled them out. But here we've then shown that regardless which c1 and c2 we choose, so even ones that don't have any factors in common, both are even, and so, well, they do actually have a factor in common. This is a contradiction. Another way to think about this is that you can always repeatedly cancel out a factor of 2 because they're always even, as this argument shows, and so you could sort of go on canceling out 2's forever, and this would contradict the fact that you can always factor numbers into a finite number of primes. So this contradiction here shows that you can't factor this polynomial into this form, which is the only form you could possibly factor it into, which means that you can't factor it non-trivially, which means that this polynomial is irreducible. And now, well, since this polynomial has degree 3 and is monic and is irreducible, it's the minimal polynomial and it has degree 3, which shows by the previous proposition we proved that the field extension here has degree 3. In particular, it's not a power of 2, so therefore it's not possible to construct this coordinate, and so you can't double the cube. Now, the final theorem that we'll look at is that it's impossible to trisect an arbitrary angle. So specifically here, we'll start with an angle of 60 degrees. And then we'll show that it's not possible to construct an angle of 20 degrees. So we suppose that we somehow had managed to trisect this angle. So we would have gotten some angle of 20 degrees. In that case, we could construct some triangle on this angle. So let's assume again that one of these sides here is coordinate, let's say 0, 1, and this is 0, 0. It's a bit slanted, but okay. Then we could, for example, draw the perpendicular here, and we now would have a triangle that looks as follows. So it has side length here, so this is going from 0, 0 to 0, 1, and then it's a right-angled triangle here that has a angle here of 20 degrees. So now more information about this triangle is that this hypotenuse here has length 1. Now we know that the cosine of the angle 20 degrees is the adjacent side, so this x here divided by the hypotenuse, which is 1. So in fact, this length here is cosine 20 degrees. Therefore, if we could trisect this angle of 60 degrees, then this cosine of 20 would be constructible. So if we can trisect 60 degrees, then the number cosine 20 degrees would be constructible. And well, hence the degree of the field extension q of cosine 20 degrees over q would be again a power of 2. So we're going to basically do the same thing as in the previous proof. We're going to show that, in fact, the number cosine of 20 degrees has a minimal polynomial over q of degree 3, and therefore the degree of this field extension is 3, which is not a power of 2, and so we cannot construct this number, and hence trisection of 60 degrees is impossible. So here we did a bit more work to construct the minimal polynomial of cosine of 20 degrees. So the first thing we note is that by some trig identities, which I'm not going to derive this formula though, is that cosine of 3 theta is equal to 4 cosine to the third of theta minus 3 cosine of theta. So if you want, you can consider this an exercise in trig identities to derive this formula. So this holds for any angle. So in particular, we have that 1/2 is equal to cosine of 3 times 20 degrees. So cosine of 60 is 1/2. And so we're plugging in 20 degrees for theta. So this means that it's equal to 3 cosine to the third of 20 degrees minus 3 cosine of 20 degrees. Well, so what does this mean? It means that, well, the polynomial, which is given by 4x to the third minus 3x minus 1/2, has root cosine of 20 degrees. Well, okay, so this implies that also if we multiply this by some constant factor, for example, 2, so we have 2 times 4, so this is 8x to the third minus 6x minus 1. This also has root cosine of 20 degrees. And well, now this is equal to, well, 2x to the third minus 3 times 2x minus 1. And this still has root cosine of 20 degrees as before. But now we can think of replacing, so we substitute 2x by some y. So we have y to the third minus 3y minus 1. And this now has root 2 times cosine of 20 degrees. So now we've converted the problem, and the reason we've done this is to make it easier to show that this new polynomial is irreducible. So the claim is that this polynomial here is irreducible. So I'm not going to show this. It's a bit more involved than the previous example, but again, you basically just kind of assume that you could factor it, then you show that, well, one of the factors would have to be linear, and this means that you again get like an expression for one of the roots of this polynomial in terms of a ratio of certain integers, and then you again make some sort of arguments about what that ratio can be, and so you show that it's not, it's like leads to some contradiction. However, this claim does not directly show what we want. So what it proves is that this is a monic irreducible polynomial that has root 2 times cosine of 20 degrees. So in fact, this is the minimal polynomial of 2 times cosine 20 degrees. So what we can conclude from this is that the degree of q adjoined 2 cosine of 20 degrees over q is equal to 3. But in fact, if you think about it, this extension here of q with element 2 times cosine 20 degrees is the same as if you just adjoin cosine of 20 degrees to q. The reason for this is that if you multiply any element you adjoin to a field, so generate the field over that element, and you multiply it by some number that's already in the field, then you could have just like canceled out this number with the inverse of it in the field, and you get the same result. So if you want, you can think about why this equality holds by proving both inclusions, but it's pretty straightforward. Okay, so again, mod this proof that this polynomial here is irreducible, which I skipped because it's not particularly interesting. We have now shown that the degree of this field extension here is not a power of 2, instead it's 3, as in the previous theorem. Therefore, it's not possible to construct cosine of 20 degrees, which means it's not possible to trisect an angle of 60 degrees, and therefore it's not possible to trisect any arbitrary given angle. Alright, so with that, we've proved all the things we've set out to prove, and I hope you've found all of this interesting. So I think these results are a nice illustration of how you can use algebra to, well, think about problems from a different domain, for example, geometry. So if you find these algebraic methods interesting, you should definitely check out Galois theory, which really proceeds from the algebraic results I presented and develops them in a lot more detail. So we've seen that whenever you have a number that's constructible, then the degree of a certain field extension, namely the field extension generated by that number over the rational numbers, has power 2. And you could ask if the converse of this also holds. So if whenever this extension here has degree power 2, then the number is constructible. That's not true quite like stated like that, but a similar result is true that uses a bit more complicated machinery, namely that of Galois theory. So you can show that whenever the Galois group of the minimal polynomial of the number you're interested in, whenever that has order a power of 2, then in fact that number is constructible. But proving that converse is much more involved and actually makes use properly of Galois theory, which needs a lot more development than the field theory I presented in this video. So I hope that if you find these questions interesting, it'll motivate you maybe to explore Galois theory a bit, because that will allow you then to definitely answer whether a given number is constructible or not.